Okay, welcome along, ladies and gentlemen, to your weekly SETI seminar talks. Today we're very fortunate to have a visitor from the East Coast come across for our Distinguished Speaker Series. That's Heidi Hammel. She's joining us to speak about the James Webb Space Telescope. Heidi did her bachelor's at MIT, Bachelor's of Science, and then went across to Hawaii, where she did her PhD. For 9 years afterwards was at the University of Hawaii. She has been spending most of her career looking at Uranus and Neptune, the icy giant planets, and using ground and space instruments to observe those. She is currently an interdisciplinary scientist on James Webb Space Telescope and on the science working group of the giant segmented mirror telescope. And so hence her connection with JWST, that she's going to talk to us about today. So if you'll join me in welcoming Heidi.
Thank you, Adrian. I'd like to share with you a status update of the James Webb Space Telescope, which is NASA's next great observatory. And I thought I'd start by talking about what makes a great observatory. And most of you, I think everyone in this room is familiar with the Hubble Space Telescope, which is the archetype for a great observatory. I wanted to share with you some statistics about the Hubble Space Telescope and why it is such a great observatory. Hubble Publications, there have been over 9,400 refereed papers based on Hubble data. That's a rate over its 21-year lifetime of 1.25 papers per day. And that rate is increasing, not decreasing. It's actually, if you just look at the last year, it's up to 2 papers a day. That's how much science is coming out of this facility. Over 340,000 citations to these refereed papers. And citations are the bread and butter of scientists. You want your papers to be highly cited. And by any citation metrics, the Hubble Observatory is just blown most other telescopes out of the water. 44 citations per day. A lot of us are looking for 44 citations in our career. One of the most important aspects of the Hubble Space Telescope is that it is a general user facility. Any astronomer who has a good idea can write a proposal to use it. Now, it's hard to get the time. The oversubscription rate varies from cycle to cycle, but after you put on a brand new suite of instruments, as happened in 2009, the oversubscription rate is very high. Your chances of getting time in the telescope are basically, 1 out of 10, something like that. Nevertheless, over 5,000 different astronomers have used the Hubble Space Telescope. And that breadth of science is what makes it such a fantastic observatory. And this is the kind of facility that James Webb Space Telescope will be. That is why we call it a great observatory. It's going to be open to the general scientific community for all to use. It's going to be in a class of Hubble. It'll be a great observatory. And for the scientists, they actually get funding to do their research. This little chart shows you over the last several years the kind of funding that's been pouring into the scientific community to do the data analysis, to write those papers. And here's where James Webb is sitting. We do have a bit of a gap here, something to think about. So who was James Webb, and why is this telescope named after him? I remember when I started working on this program, when I was selected to be an interdisciplinary scientist, it was called the Next Generation Space Telescope. And one day we got an email and said, your telescope is now the James Webb Space Telescope. So I did what anybody would do. I Googled James Webb, because I was too young to know that James Webb was NASA's administrator from 1961 to 1968. About the age of these young people over here. Do you know who the current NASA administrator is? See? All right. So I didn't know that. It's Bolden, an astronaut, Charles Bolden. He was in charge of NASA when I was your age. He was the architect of the Apollo program. He was the person who made that a program of putting a man on the moon and returning him safely to Earth a reality. But more importantly for the scientific community, he initiated the space science program at NASA. And during his tenure, there were at least 75 space flight missions exploring the planets. He was a very strong advocate of science. And that is who James Webb was, and it's an honor to have our telescope named after him. Now, what is the James Webb Space Telescope? It's not a telescope like you've seen before, probably. This telescope is designed not to work at visible wavelengths of light, but to work at the infrared wavelengths of light. And those are wavelengths of light that are longer than we can see. And infrared light has another name. In fact, it's called heat. Heat. We are using this telescope to measure the heat of the universe. But the Earth is pretty warm. So we don't want this telescope on Earth. And in fact, we don't want this telescope to get warm at all. So we have these layers here to protect it from sunlight, Earthlight, moonlight. And there's no tube on this telescope. I didn't just leave it off the diagram. This is what the telescope looks like, because the tube that encloses a telescope is warm. It radiates heat, and we want to have as little heat as possible. And so that's why we design it in this sort of very exposed system here. So we have a sun shield, we have a primary mirror, and I'll show some more of this later, a secondary mirror, and this primary mirror is segmented. And we'll show more about that later too and what that means. So it's a very different kind of telescope. Why are we building Webb? We have 4 different kinds of science themes, sort of the whole universe encapsulated in 4 different themes. We want to look back in the history of time in the universe to this era right after the Big Bang. Not at the Big Bang, but afterwards, when the first stars started to shine. And Hubble can't get that far back in time, but Webb will be able to do that. We're going to look at the very first galaxies and how they assembled over cosmic time. We're going to study the birth of stars and planetary systems. And we actually want to look for planets around other stars and try to characterize the atmospheres of planets around other stars. And all of that science is what we're planning and building and designing this telescope to do. But I have to say that this is a general user facility like Hubble. And when we look back on the last 21 years of Hubble science, the stuff that we planned to do with Hubble more than 20 years ago is about half of the top-ranked science that Hubble did. The other half of the top-ranked science produced by the Hubble Space Telescope is stuff that nobody even thought of or anticipated when we built the telescope. And that is what makes a telescope like Hubble or Webb a great observatory, because we're building it to do this kind of science, but we know that some of the most exciting science that's going to be done is something that the young people in this crowd are going to think up that we haven't even thought of yet. It's very exciting. I'm really not going to talk a lot about the science today because I want to tell you about the telescope itself. I want to show you the parts and the pieces and how it's all coming together and give you a status update of this telescope. And let me show you how it compares with Hubble. This is the size of Hubble's mirror, 2.4 meters. This will be the size of Webb's mirror, 6.5 meters effectively. It's not a circle because it's not made of a single monolithic piece of glass like most telescopes are. It's made of segments. Most of our modern telescopes today are segmented. They're not one piece of glass. And we do that because we can adjust the positions of these segments in real time to make the telescope the shape that we want to make it. And so if there are problems with the shape, does that sound familiar? Like with Hubble, we are able to adjust the shapes of these mirrors. And we also use, okay, that's fine. And this little one over here, if you can see it up there, That is the Spitzer Space Telescope. This is another infrared telescope that is in flight right now. And you can see that just that one mirror is smaller than each of the segments that are going to comprise the Webb Space Telescope. These pictures underneath show you the field of view of the cameras of Spitzer and over here Hubble. And then these are the fields of view that we will have for the James Webb Space Telescope. So somewhere in between these two. And this chart is a representation of the wavelengths of light that we will cover. Here is the this is the electromagnetic spectrum. This is visible light from the rainbow of light from indigo through the red. And this is Hubble's coverage. It's mostly a visible wavelength telescope. A little bit beyond visible into what we call infrared. But the James Webb Space Telescope will start at about 6,000 angstroms. That's red light. And it'll go from the red all the way into the infrared. So it overlaps Hubble and it overlaps Spitzer, but it's a much larger telescope than either one of those two. Where will it be? I already said it's not going to be at the Earth. In fact, we're going to put it really, really far from the Earth. We're going to put it at a gravitationally stable point called the Lagrange 2 point. And how does that compare to Earth's moon? Well, there's the moon to scale. Now, you know where our astronauts can go today. They go to the space station. And the space station is about that far away from the Earth. So we were able to send people to service Hubble because it's in orbit around the Earth, low Earth orbit. This telescope will not be serviceable by the technology we have today. So we have to get it right the first time. We will. What are some of the key design features? Well, I already told you about its segmented primary mirror, and it's got this sun shield that will protect it from sunlight, keep it cold. It's going to be operated with solar power. This is solar array on the bottom. And all the instruments will be behind the telescope here in this integrated science instrument module. The stuff down here is the spacecraft itself, the things that keep this thing moving around in that orbit around the L2 point. How will we launch it? We're going to launch it on an Ariane 5 Heavy. This was provided to us by the European Space Agency for free, but I have to say that the process of redesigning it to fit in the rocket fairing took quite a bit of effort, and the moral of that story is there's really not any such thing as a free launch. The telescope does not fit inside the rocket fairing in its deployed configuration. We have to fold it up to fit inside the rocket fairing. Even though this is a very large rocket, you can see that it's folded and stowed for launch. And then after it is launched and on its way to the L2 point, it has to open up. And we have a computer simulation of that here, so you can see how that works. The first thing that happens is that the solar panels come down on either side, the pallets come down, and then they open. And then you can watch as they start to deploy off to the side. They're just on pullers and levies. It's just wires pulling these things out. And once one side comes out, then they pull the other side out. Now, it's many layers. Remember what your mother always said to be insulated. Wear layers, wear layers. It's the same thing. If you watch carefully now, you'll see that this starts to separate. First here, and then there. And then it comes back and separates again and again. And it does this repeatedly until all the layers are separated, because you want this insulation to protect this from the heat of the sun. After that, you will see a little trim tab come out the back. That's for momentum stabilization. Then comes the secondary, and the two wings of the primary come out, and you have a telescope that's ready to roll. Now, I have to tell you that every time I see this, I'm terrified. Oh my goodness gracious, how many moving parts are there? And what if that secondary doesn't deploy? You're dead in the water. What if those wings don't come out? It's just absolutely terrifying to me. We talked to the people who are building this. It's Northrop Grumman is the prime contractor, and they say, don't you worry, we've done thousands of deployments in space. Can't tell you what any of them are. But we've done them, and so we have to trust that they have, in fact, done all those and done them correctly. What are the science instruments? There are 4 primary pieces of equipment that we will use to study the universe with Webb. First is a near-infrared camera. We also have, and this is being provided by a combination of ESA and the University of Arizona. We have a near-infrared spectrometer, which is being provided by the European Space Agency. We have, I'm sorry, NearCam is European. This is the only US instrument. This is being provided by the University of Arizona. MIRI is a consortium with Europeans and University of Arizona, mid-infrared imaging camera. And this, the fine guidance sensor and tunable filter system, is being provided by the Canadian Space Agency. And that is the thing that will actually be used to do the guidance on the system. So we have a true multinational observatory here. Let's talk more about these instruments, because I know there are some astronomers here who might want to actually see some details. So I throw them up there for those astronomers. And I'm showing you flight hardware here, so that you can see that this isn't a PowerPoint telescope or PowerPoint instrument. We actually are building these pieces of equipment. The near-infrared camera will be operating from 0.6 to 5 microns. That's from 6,000 angstroms out to 50,000 angstroms. Has a variety of different resolutions, a pretty big field of view. And anybody wants to ask me more questions about that later, I will. Because I've got a real mix of audience here, right? Because I've got kids who don't want to know all these details. But I have astronomers over there who were asking me these details at dinner. So we will have the near-infrared spectrograph. This is actually a really cool instrument. When in astronomy, when we take pictures like this, so you see these pictures, but what astronomers really want to do is the pictures are great, but they want to measure the spectra. They want to see the light at all the different wavelengths. And so what they'd like to do is take a spectrum of this object, that object, that object, and that object. And normally you can't do that. But what they're building for Webb is this device called a micro shutter array. And it's an electronic device that has all these little tiny shutters. And I want to give you a sense of scale here. One of the little tiny issues that we're having right now is they found some fibers on here that sort of look about the size of my finger, but in fact they're like little pieces of hair, to give you a sense of scale here. So imagine all these little shutters, and we can open and close these shutters. They're called micro shutters, so that we can take a picture like this and keep most of it closed off, but just open the shutters on the objects that we want to get our spectrum for. So it's a very nice, interesting new piece of technology that we're developing for James Webb Space Telescope. And there's a whole lot of other details for those of you who are really interested in that kind of thing. And here, again, is actual hardware for you to see. The mid-infrared imaging system is going to be a really interesting camera. And this is one of the things that I'm very interested in using to study outer planets. And here it is on its bench at Goddard. It's going to have a large, my thesis advisor's in the audience here. He remembers when we had to do imaging in the infrared with bolometers, one measurement at a time. And here we have arrays that are 1,000 by 1,000. I mean, that would have taken years of time, and we'll be able to do it just like a snap. So things have come a long way in my lifetime as an astronomer. The fine guidance sensor, tunable filter images. Again, this is some very interesting technology that we've been working on. I'm not sure we've ever flown it in space before, these tunable filters. Instead of a piece of glass that filters out the light, you can actually tune the wavelength of the filter to exactly what you want it to be. And so you can see that here going into a test chamber. And it will also be able to do direct imaging as well. So who is making Webb? I thought I'd give you a sense of that. The Goddard Space Flight Center in Maryland is the mission lead. Strong collaboration from the European Space Agency and the Canadian Space Agency. As I said, we got our free launch from the Europeans, and they are also helping build cameras. Canadians are building the fine guidance system. Northrop Grumman Space Technology is our lead spacecraft contractor. Space Telescope Science Institute, where Hubble is operated, is doing mission operations for James Webb as well. To give you a sense of scale, I've shown you these pictures, but you don't get a sense of scale how really big this is until you see a picture like this. These are the people just at Goddard who are working on this program with a scale model built by Northrop Grumman. And those sun shields are the size of tennis courts. So this is quite a large spacecraft. What about the optical design? This is for people who care about this sort of thing. I put it up there so you can see it. One of the things that I haven't said yet is that because we're measuring the heat from the universe, our telescope itself has to be cold, really cold. 40 Kelvin, not 40 Fahrenheit, but 40 Kelvin. That means something like minus 200 Fahrenheit. And it's that cold in outer space. That's good. So we're going to be passively cooling the telescope. In other words, it's going to be sitting out there radiating to the black of space, and that's how we keep the instruments cold. And we put those sun shields between us and the telescope and the sun. There's a lot of issues when you're working at 40 Kelvin, though. Because your materials, think about this, you're taking metals and things that you're building your stuff out of, and you're cooling it to minus several hundred degrees. And so one of the reasons we picked a special metal to make our mirrors, beryllium, we picked it because it does not change its shape with temperature. Because we have to build this thing to withstand temperatures, room temperatures here when we're testing, and the cold of outer space, and yet we have to hold the tolerances to the widths of human hairs. So it's very, very challenging technology. There's all kinds of details that I can share with you if you are really interested. I actually gave the talk just like this to the New England Astronomy Forum, Northeast Astronomy Forum, which is all amateur astronomers. And this is what they want to know. What kind of a primary mirror? What's the F ratio? There it is if you're an amateur and you want to know that. Let me just show you some hardware. I just love hardware. It's what I like. There's the mirror. This piece of the hardware is the aft telescope system. And that's where we have a lot of lenses. I'd like to show it because it's built. Inside it, you can see the secondary of the tertiary mirror. You can see the fine steering mirror. These mirrors are what we call rubber mirrors. You can move them. They're not solid. I mean, they're flexible mirrors. And so you can do adaptive optics work with this. So if your telescope has vibrations, let's say you moved it and it's still settling down, you can use these mirrors to take that kind of effect out. What about the main mirrors? This is one of the most exciting things that's going on right now. They're made of brushed Wellman. They're big pieces of beryllium. Beryllium is that metal that does not expand and contract with temperature. It's a pretty dangerous metal. And so people are wearing gloves. You can see here in this picture. This is a blank. They take this, they form it out of beryllium pellets, then they saw it in half, and then they polish it. They also lightweight it. They take out, basically, they honeycomb the back of it, leaving just the front surface, and they effectively take away 92% of the material. So it's very, very lightweight. And then they polish the surfaces, and they coat them, and they ultimately coat them in gold. And we don't do that because we want them to look pretty or we want to spend a lot of money. We do it because gold has a property called very low emissivity. And that's what we want for an infrared telescope. All right? That's why we coat them with gold. And I wanted to show you a picture of an early engineering test where this is what we call an engineering demo unit. It proceeds all the other mirrors through all the testing processes, through cutting it, lightweighting it, polishing it, coating it. So it's always one step ahead of everybody else, and that's why in this picture it looks different. This is a picture where it was the only one that had been coated in gold, and they are about to drag it into this very large cryogenic facility where they'll take the mirrors down to that 40-degree Kelvin temperature. Here's a picture of them dragging the assembly in. They actually pull it in with cables. Just about a month ago, this picture was released. And these are all flight mirrors. These are mirrors that are actually going to go up in space that have been coated and are being tested at cryo at this X-ray cryogenic facility at the Marshall Space Flight Center. And this picture has been distributed a lot of different places. It just appeared on one of the astronomy pictures of the day sites because it's just such a gorgeous image showing all these coated mirrors. And you remember that this is only 6 of 18 mirrors, but we anticipate that these mirrors will all be done by, I believe, July of this year. The mirrors will all be completed. Here's another 3 of the mirrors, the fine steering mirror, the tertiary mirror, and that engineering demo unit. Here's a picture of that, and here it is about just coming out of the coating chamber for this particular mirror. There's a status update as of, when was this? This is about a month and a half ago. And you can see many of the mirrors are ready for flight. So that's great news. They're all on schedule. Everything's going well. Will we have good images? People ask us a lot. Will you have pictures like Hubble does? And the answer is yes, we will. We will have very good pictures. We have done simulations of what we anticipate. These are some pictures, and what you need to know is that when you look here and you can see little boxes, those are the actual pixels, the detector elements, and we are getting very high quality images, and we anticipate. You never know for sure, but looking at the systems that we have now, we anticipate we will be getting down to exactly what we predicted, and we'll just have to wait and see. 0.032 arc seconds in the NearCam. It's wavelength dependent, so which color you look at tells you exactly how much, what the spatial resolution will be. Here are some more simulations, and everything is looking very good for that. So we will have terrific pictures. How are we going to test this? This is actually the most difficult part because we have no facility on the surface of the Earth in which we can deploy those sun shields that are the size of tennis courts. And we only really have one facility that's large enough to do testing of the 6.5 meter mirror, and that's a facility at the Johnson Space Center. And here's a picture of the facility itself. And here is a sketch of how we are going to test the mirror assembly inside that facility. I'm happier with this because our earlier design actually had this whole thing suspended at the top of a huge scaffold, which was really scary to me. And also it was a huge complex engineering job to design a whole scaffolding system to do it. So instead we have it sitting down here in what we call a cup-up configuration. And we test something like this with lasers. That's how we actually do it. We shine laser beams up off a variety of equipment here and here, and then we do all sorts of measurements to make sure the alignment of everything is working properly, that we can do the phasing of the mirrors to make sure they're all working together as a unit. We have a 1/6 scale model at Ball Aerospace right now that we are using to test all the specific software and codes. We call it phasing algorithms. And we're using our 1/6 model to develop the algorithms so that when we're ready to put this in the test chamber, that will already be ready to go. And so that's on the plate right now. So but it's very complicated. It's the hardest part of this mission is the integration of putting all the pieces together, the integration, and then the testing to make sure it's all going to work. Can we see some more hardware? Yeah, you can. This is what we call the Pathfinder Backplane. This is the back end of the telescope. It's a Pathfinder because it's not the actual flight hardware, but we build it so that we can learn how to build the actual flight hardware. I mean, if you're going to like make a mistake and break something, you want to break it on your Pathfinder, not on your actual thing. And it's always hard to get a sense of scale here. But if you look along the sides, you see like railings. You can imagine a person standing there. It's pretty big. This is the thing that the mirrors will be mounted. This is a test bed for the structure that the mirrors will be mounted onto. Here's a 1/3 scale model of that sun shield, where they're testing how you actually manipulate this material. I've actually stood next to this particular model down at Northrop Grumman just several months ago, and it's only 1/3, and it's a pretty big piece of hardware. Here's a testing of a actual scale model where they're practicing folding it up and then pulling it out, and you can see the people inside there to give you a sense of scale. This is the backplane. It's a mock-up of the backplane, and they use this to practice folding things up and letting them down, making sure everything's aligned properly, to make sure that everything fits together. And you saw this piece before, and now you're seeing that piece integrated with the pallets that hold the big sun shields that come out. And this is the actual science instrument module itself, and that's where all the pieces of equipment, all the instruments that we're going to use the telescope, they're all going to go inside to that piece. All right, so that's a lot of hardware. How much will it cost? This is the question that everybody asks, because there's been a lot of reports that this telescope's going to cost more than you think. And it got to the point last year where it was clear that it was going to cost more than we had anticipated. So Senator Mikulski put together a panel, and that panel wrote a report. They were told to find out several things. The report came out in November of last year, and they were asked to do 4 things in this report. And the 4 things were this. Find out, number 1, what the causes were of the cost growth and schedule delays. 2, what are the plans to actually complete the telescope? 3, what are the changes in the cost and schedule that would allow this telescope to move forward? And 4th was, what is the minimum cost to actually launch this telescope with an actual launch date and a budget profile? So that's what this commission decided to do. So, just so you know, this is language from the report. There were 2 mistakes that led to the cost growth. The first was that the budget was wrong at the time that this mission was confirmed to start. It was wrong. They had not done a full, what they call bottoms-up estimate, and they knew that there were some issues with some things like integration and testing, and they did not put in enough reserves to cover them. All right, so that's bad. That was wrong. Did it wrong. But 2 was that NASA management missed this error. They were not evaluating the budget closely enough to catch that error. So there was 2 things. You did it wrong, and you didn't find out you were doing it wrong, and you shoulda. So that was the root causes. And it's actually a really well-written report, and it's all publicly available. You can go look if you don't believe me. 2, plans to complete. First thing that they said was that the hardware, which is what I've been showing you today, is actually progressing very well. It's on track. There were 10 very challenging technologies that we were adapting for this that had never been done in a space mission before, and all of them have been successfully moved forward. However, major uncertainties remain in this integration and testing that I've been discussing. And in fact, there was a completely separate group, a test assessment team, that was put together just to study that part of it. And they had a number of specific recommendations and suggestions and things we could do better or could do shorter for less cost. And so those things are all being adopted. 3, how do you avoid cost increases in the future? First of all, take Webb out of the astrophysics division and make it completely separate at NASA headquarters. And that's what's been done. It used to be the NASA administrator, who these young people now know is Charles Bolden. And under Charles Bolden is the Science Mission Directorate. Under that is astrophysics. In the past, under that was JWST. Now, you have the administrator and the Science Mission Directorate, and JWST is separate. So it is not buried here. The science of the program is still under astrophysics, the science that will be done. But the program, the spacecraft itself, is a separate program that's been elevated up to a much higher priority within NASA. What else? They said to do some restructuring. This is all management type of stuff at Goddard Space Flight Center. And these things have been done. This has certainly been done. You've assigned the project directly to the Goddard Space Flight Center director. Establish an Office of Independent Program and Cost Evaluation. That's to that second bullet where you missed the problem. To my knowledge, that hasn't been done yet. That's really for future missions in any case, not for this one. And finally, develop a new cost and schedule plan. This is where the rubber hits the road, and this is ongoing right now. It's happening right now. I've just actually checked today so that I would have the latest information for you. It's gone through the NASA process, and it's being iterated up at higher levels in NASA. But we don't have a number and a date to give you yet. I can tell you this, that this report, John Cassani's report that I've been discussing, had an estimate. And their estimate, based on what they knew as of November of last year, was that to achieve a 2015 launch, this program would cost $6.5 billion. However, that required additional $250 million in FY11. Now, any of you who've been paying attention to what's been going on in Washington with all the continuing resolutions, it's very unlikely, I think, that we would get this kind of funding in FY11. And therefore, it's unlikely that we'll be launching in 2015. It'll be later. And anytime you move a program later, it costs more because you have to take your whole, what we call a marching army of engineers and scientists and programmer people and all those people, and you have to make them work for longer, so it'll cost more. So what's the final answer going to be? We should probably know by September. Like I said, I think that some people have an idea now, but none of it's public information. But my guess is it's going to be later than this, and it'll be more than that. Oh, for context, how much did Hubble cost? Hubble, if you look at its full life cycle cost, that means from soup to nuts, including all the science that we're doing too, it's currently more than $10 billion. So my takeaway message from that is, if you want a great observatory, you have to be willing to pay the price that it takes for a great observatory. It just costs a lot to do transformational science. Is it worth it? I obviously think it's worth it, or I wouldn't have spent the last 5 years of my life doing this and plan to spend the next 5 years or more of my life doing this. I have a video to show you, which was put together by a fellow named Hank Green, who has absolutely nothing to do with the James Webb Space Telescope. And none of us who work on the project ever heard of this guy until this video went viral in the astronomical community. And so I thought I'd share it with you because he says it all much better than I could. And like I said, he has nothing to do with the program. He just found a whole bunch of stuff on the internet and put this together. So I'll share it with you now. So, the James Webb Space Telescope, it's making excellent technical progress. It will require significant commitment on the side of NASA and our international partners to finish and operate. However, it will enable an astonishing range of science across all fields of astrophysics. And it will be the dominant astronomical space facility for the next decade, just as Hubble has been for the last 2 decades. And I hope to be in French Guiana sometime in the next decade to watch this launch. Thank you very much.
Okay, if I could just start with the first question, Heidi. Are there any fallback modes if something doesn't expand correctly? Is there a set of fallback modes expected for various aspects of the primary mirror? And could you tell us what sort of thinking has gone into contingency modes?
Well, if the question is, what are the fallback modes? What happens if your mirrors don't open up or your solar panel doesn't deploy? If the secondary mirror doesn't go out, then there's nothing we can do because we don't have any optical path. If other aspects of things don't work, we just have to work with whatever that aspect is. Just like when Galileo, the Jupiter mission's antenna did not open up, well, you had to work around that. It'll depend on the failure mode that we have, what we do to solve it. If something doesn't open, just like we do with Galileo, you try jiggling it. You try electronically cycling it. Every piece of everything that could go wrong, there's going to be something that you're going to try to fix it. But yeah, it's a scary thing. But if you're going to be doing state-of-the-art cutting astronomical space facilities, you're working at the edge. And you have to be willing to take the risk. And we'll do all the testing we can here on the Earth to make sure that things don't go wrong. But space is a risky business. Sir.
Sorry.
Okay. You mentioned a trim tab. What does it do and how does it do it?
That's a momentum trim tab, and it's a one-time thing. Once this is deployed and we understand how it is operating in space, it's set at the proper angle to have. I'm sort of drifting far afield of my knowledge because it's a space engineering thing, but it's a one-time adjustment to properly align the momentum distribution in the spacecraft. So it's set once and then doesn't change again. Sir.
Suppose it all goes well and it images a planet, Earth-sized planet, 25 light years away. How many pixels will that planetary image get?
That's a good question, and maybe Mark, you can help me with that because I don't think it's going to subtend many pixels at all. It's more that we'll be able to measure the chemistry of that planet's atmosphere, not so much doing any spatial resolution. So we'll be able to measure composition in the atmosphere. Even the giant planets, we won't really have any spatial resolution.
So this is more spectroscopy than image.
It's spectroscopy. That's where the action is.
I'm like you. I try not to think too much about all the moving parts of this thing, but I just have some questions I have to ask. What are the shields made of?
They're made of kapton.
Okay.
Which is a very thin material. It's sort of, the best analogy is it's like the Mylar in the potato chip bags, but stronger. You know what I'm talking about? The metal,
Yeah.
metallic, yeah, it's stronger than that. What's that?
You can rip apart a potato
Yeah, well, I'm sure if you tried hard, you could rip Kapton, but it's stronger.
And my last, and I promise I'll give the mic back. The mirrors are open. What are we doing to protect those surfaces from micro meteors or any debris or?
Space junk, micrometeorites. Yes. We're not doing anything to protect them. It's just going to go up in outer space and they will be exposed to the elements there. However, we have done studies of the space environment, near Earth space environment, certainly. We understand that fairly well. And we are also doing analyses of what if you lost a mirror? What if you had, debris that hit it, or how does that degrade the telescope? And we don't think that's a major problem for this telescope. Out at L2, it's not like low Earth orbit, which is filled with debris. Space is pretty empty out there. So that's not one of our primary concerns. But we are doing engineering analyses of that.
My question is, have you looked at an inflatable method for deploying the sun shields?
I haven't. No, I believe that they're working with technologies that have already been demonstrated in space for other applications. And I think that it's all gears and pulleys, the technologies that I've seen demonstrated, not inflatables. So that would have been if we were going that route, that would have been probably on our list of top 10 technologies that needed demonstration before we could proceed. And so at this point, we won't be going that route.
Two kind of cost questions. One is, you mentioned that Hubble cost $10 billion, but also all this tremendous science. Does the Hubble project have a cost recovery system such that you can say, yes, it cost that money, but the money came from these other places, and therefore Hubble made a profit? And or, how about James Webb?
We don't do science usually to make profits. So how do you define profit? You could see the number of papers and citations, and that's scientific knowledge, but I'm not sure how we'd put a dollar sign on that.
I'd collect from the people who wanted to use it.
Well, that doesn't work. That's why we have the federal government building these things and industry not building them. The taxpayers are building it. It's the public's telescope, effectively.
I'm sorry, I did have one other question, and that is, you mentioned that we have partners, European and Canadian
Yes.
partners, and that we had a $6 billion bill. Are they paying part of that, or was that $6 billion the U.S. part?
That's the U.S. part.
And so the total might be?
No,
I think the answer
right.
is that the US owes the $6.5 billion, and I think the Canadians and the Europeans are donating in kind with their time and their instruments and their
launching. This is the cost. This is NASA's cost for this telescope. That's the number, because this has to be paid for from NASA's budget if NASA wants this facility to be flown.
We might have to follow up with a question afterwards.
Yeah, I just wanted to ask about going back to the comment you made that space is pretty empty there. But I was wondering, I don't know much about the Lagrangian points, but wouldn't they in fact be sort of the sucking area that would collect small pieces of debris, micrometeoroids or whatever? Is that not the nature of the Lagrangian points?
No, that's not what Lagrange points do. Lagrange points are gravitationally stable in that if you put something there, then it's not likely, it can be stable there. It's much easier to think of Lagrange 1 because you have the sun and the Earth, and Lagrange 1 is in between, and it's the point where the gravitational pull from the Earth equals that from the sun, right? So you put an object there, it stays there. 2 is a little harder, but it's the same thing, all right? But we go in orbit around 2. There are other Lagrange points too. It's like the guy said in the video, I really don't want to try to explain Lagrange science right now, but it's all out on the web for you if you really want to follow up on that.
Next question, how do you plan to use James Webb to advance your research on outer planets?
Thank you. That's a wonderful question. How do I personally plan to use it? Why am I spending all these years devoting time to this mission? My research is studying outer planets in our solar system, and they are cold. Uranus and Neptune are cold objects. They're very hard to study from the ground. Even with our largest ground-based telescopes, we were trying to look at the upper atmosphere of the planet Uranus, and we spent hours and hours and hours at this telescope. And at the end, my colleague said, well, Heidi, there's your definition of zero. We got no signal after 7 hours because it's so cold that you just don't get enough heat. And so this telescope will allow me to actually image the planet Uranus and study the atmospheric circulation in this planet. And I can't do that from the ground with the telescopes we have now. We will also be able, in our solar system, be able to use this telescope to study the chemistry of objects in the Kuiper belt. That's that realm of bodies beyond Neptune's orbit, where Pluto resides with his 10,000 closest friends and relations. And those objects, again, are extremely cold, so we need to have a large telescope like Webb to actually study the chemistry on the surfaces of these. And we can do it for Pluto, and we can do it for Haumea and some of the largest objects, but to see the smaller ones and actually study chemistry, we need this big space telescope to do that. So I'm looking forward to that. I'm also looking forward to studying the atmosphere and the surface of Saturn's moon Titan. One of our other interdisciplinary scientists is Jonathan Lenine, and he's going to be leading that charge. There's just a whole lot of different science that, don't get me started on comets too. The chemistry of comets is really, there's so many amazing things that could be done. I'm really looking forward to it.
My question is about what other departments within NASA might be looking at a rescue mission of some sort, perhaps using robotics, if not people, if in case deployment fails. There's a lot of robotics studies, and maybe there can be some synergy between, as a test of their robotic skills, they could go rescue James Webb.
Well, I would say if a problem happens with Webb, because it won't, all right, but if it ever did, then that might be something for a target for people who like that thing to think about. But we're not planning that at this point in time because we're working to a success-oriented model here. But I can see that one can imagine, not just for Webb, but for a lot of the facilities. There are other telescopes at L2 right now. Several people have said that would be an interesting place for astronauts to go someday, is to L2, to work with Webb or other telescopes there, bring them back, who knows. I don't know. It's just not part of this program. That would, as you said, that's a different part of NASA. And so that's not part of this.
You could send Bruce Willis.
You could send Bruce Willis, right? Riding a rocket.
One question back to the kind of engineering issues there. Like as you mentioned, the Galileo kind of incident there. People are visual in their debugging capabilities, and probably a lot of people would have given an arm and a leg to see how that whatever antenna in Galileo was kind of mocked up. Would it make sense to have some small baseball size little camera, like a webcam, being there that looks at this thing and gives people visual cues on deployment phases as things kind of complete, and God forbid debugging capabilities if they're stuck in some step.
Yeah, so I'm gonna take the clip of that and play it for the people who I've been repeatedly saying to that we need to have little engineering cams on those booms so that when the solar arrays are going out, or when the sun shields are going out, when those things deploy, I just saw, did you see the Japanese spacecraft that had the webcams, the little engineering cams, where you could actually watch their things deploying? I'm like, you know, why can't we just get one of those little things that like at, you know, Best Buy and stick it on there? You know, oh, well, yeah, you can't do that. I'm like, we got to do it. I wish that I could convince people that we need to do that, because I've said that myself. It's just not in the engineering spec right now. It adds to cost. You heard before, cost is an issue. But I fully agree with you. And the last time I brought it up, which was about 8 months ago, I was told, this isn't the right time to bring that up again. Okay, all right, well, I'll wait a little while. You know, but I agree. I totally
Heidi?
agree. Yes.
Question.
This is Phil, who I went to graduate school with.
Thanks. 2 questions. One, the fuel lifetime on this was, did you say 5 years?
Yeah, the hydrazine that we use for station keeping, to keep this in orbit around the L2 point, it's technically 5 years goal, 5 years with a potential goal of 10 years.
Okay. And it's passively cooled, right? No
Yes.
cryogens? Okay. And one other question. Beyond what wavelength is it diffraction limited?
And there is a cryo cooler in the mid-infrared camera, I believe, but there's no cryogens. And its diffraction, it's beyond 2 microns that it's diffraction limited.
So when it's launched in year X,
Yeah.
how long until we actually see something coming back from it?
My guess, based on my experiences with Hubble, it's several months to get there. It's several months to do all the commissioning and checking out all the equipment and getting everything stabilized. So my guess is it would be probably 5 to 6 months before we have the first images released, which is consistent with Hubble. When we did the last servicing mission in May, then in September was when we actually had the big press conference with the early release data. Now, it just so happened we actually had a comet crash in between, but what's up?
Does it get there that quickly? Because it's flying a long way.
Yeah, it goes pretty fast, though. It's a big rocket, the Ariane.
Okay, if you've got any more questions, I'd encourage you to come up here and take them up to Heidi after the talk. And Heidi, we have a special antique SETI mug to commemorate your talk.
Thank you very much.